Okay, today I'm going to start to talk about the centroid of the composite body. Previously, we were talking about how we can find the centroid of any object that we are given and look at how we define an element and use the integration to find the centroid of the body. But sometimes the body we have is made of some familiar shapes. For example, what if the body we have, or what if the surface we have can be splitted into the rectangle or triangle or trapezoid or those kind of familiar shapes. In those conditions, uh, we can use a easier approach to find the centroid of that composite shape. So, for example, if we have an let's say an area that looks like this, we have an area that looks like this. If you look at that, we can go ahead and actually split that into two familiar shapes. So we can go ahead and say, okay, I'm gonna split it into two shapes. Is one of them is this one is the rectangle, and the other one is just this one, which is going to be the triangle sitting next to that. So we can always do that and say, hey, we have two different body here, two different shapes. But the thing is that those shapes, the rectangle or triangle, we can easily do the calculation and uh, find whatever find the centroid for those of them. Similarly, if we have another shape, for example, like that, if I have something like that, again, if you look at that, I can go ahead and say, hey, that's, I can split it into rectangle either from here or here, as you might do it from here. So I can split it into rectangle, and then I have the two familiar shapes. So one of them is the rectangle here, and then another one is the rectangle on the top. When we are dealing with these such cases, the integration changes to summation. For example, if I have and we know that we have uh, the centroid is integration of the um, dA, and then in such cases we can replace it with the simple summation instead of integration uh, over sigma a. The same for the y, the centroid of the body in the y direction. So instead of having it for each element and then do the integration, we will have it the same thing, but we do it by summation as that. Similar to what we have here, we can do that uh, with the line. So assume if I go ahead and we will have a line that's familiar. If we have a line that the shape of the line is familiar to what we know. So for example, assume we have a straight line like this, and then we have the half a circle. Then we have a circle. So again, the same as before. Well, can go ahead and split it into two known from these points. So I can go ahead and split it in 2 point, two lines that almost I know everything about them. So one of them is just a straight line here, so I can get one of them, and then the other one would be that section on the top. It's a half a circle. So I can also say that this is the part that we know and we can do that. So it's either we can do this like what we did previously and do the integration, or we can split it into two. If we can split it into the known familiar shape with the same as before here, the centroid for the line was the centroid. We do the integration for the element, and then we replace the element with any of these single parts. So it's gonna be, oh sorry, these are dl, so it's gonna be dl or dl, and then we replace it with the sigma. And the same in the y direction. So we can go ahead and say, okay, this is, again, we do the integration for the element, or then instead of doing the integration, we can replace it with the simple summation. And then in an example, we'll see how we can do that. There's only one point about this method, and it's if you are dealing with the known shapes, but what if there is a hole in it? If there is a hole in the whatever we are trying to find its centroid. So assume this one, the one we have here, I will draw that again. So assume I have that. So assume I have that, but this time a similar shape to that. But this time I have a hole sitting somewhere in that, like this. So that's the shape, and then there is a hole in it. If I look at that, so probably I will say that, okay, yes, I know this, I can split it in two known shapes, but then there is a hole in there. So what I'm gonna do with that hole? So before doing that, let me add some axes so we can do it. So assume this is the x-axis here, and here is the y-axis. What we will do in those cases is that I will go ahead and split it into two shapes. So I will say that this one is equal to a full shape that we have, like this. Make it bit. So there's one like the before, but this time in the full shape. There's no hole in it. And then these are the axes. And then we have another one. So that's the x and y axis. And this time plus this hole. So if I put the hole exactly where it is, so we have the hole. So it's gonna be that plus the hole. Then here we have the solid object, there's no hole in it, and I can go ahead and split it in two known shapes. So here I can go ahead and say, okay, I will split it into two known shapes. So it's gonna be in one rectangle and one triangle as well. So one rectangle, and then I have this part, which is the hole. The only point that about this part I have to remember is that because this is the hole, the area for that hole, because it's a hole, the area for that hole is negative in a calculation. So the area for hole is negative. So whenever we are doing this calculation here, and we add the area together, or we calculate the sigma xa or sigma y. In those calculations, we just use the negative value for the area because actually that area is not there. So I can go ahead and uh, in other words, if I have a solid, I have a shape that has a hole, I assume the hole is not there, and then I split it into whatever shapes, the familiar shapes I have, and then also I add it with the hole, and I will consider the area of the hole to be negative. Now let's look at an example, see how we can calculate the centroid of this composite body. So to do that, we can go ahead and um, split that body into the known shape. So first I will go ahead and say, okay, the known shape that I have this. So I would have this triangle there, and then I will split it also here. So I have these two rectangle also on the right hand side of that. Then I will go ahead and find the centroid of each of these uh, shapes. So for that uh, uh, rectangle, we know that is sitting somewhere here, and the distance of 1/3 from the base. So this distance here is 1/3 times 2. So it's going to be 1/3 of that. The whole base is 2. And the same here, because this distance is 2, so it's going to be 1/3 of 2. So it's going to be again 1/3 of 2. For this one, for this rectangle here, what you have is the distance here is going to be half of distance, so it's going to be half, and here again it's going to be half of distance there, so it's going to be half. For this one, it would be sitting somewhere here, and this distance then up to that point is half of 2, so it's going to be 1, and the distance up to that point is also, so we have 1 plus half of the 1, so it's going to be 1.5 to that, so it's going to be 1 plus, so it's a 1 up to this point and half of that, so 1.5. So now we divide this into the three shapes, and I'll go ahead and name this. I would say that assume this one, uh, the one the triangle is gonna be 1, and then this small 2, and this top rectangle is gonna be 3. So we have these three uh, objects there. Now that we have separated all of these in the segment and we have their centroid, we will go ahead and calculate the um, centroid of that body. So we'll start with writing the segment 1. So we have segment, so the segment 1, and then for that segment 1 we calculate the area. It's going to be a square meter, and for that triangle here is going to be half of base times height, 2 times 2, so it's going to be 2 square meter. And then we will have the centroid for that triangle. So in the x direction, it's going to be 2/3. It's going to be 2/3. But if you look at that, it's negative because it's on the left side of the origin, so it's going to be negative 2/3. And in the y direction, it's going to be positive 2/3. And then we will have it times these two columns by each other, so and the result would be, the unit would be meter cubed, and remember that's the unit comes as a result of multiplying these two together. So that is going to be negative 2/3 times 2, negative 4/3, and then the same for the y direction. So it's going to be 2/3 times 2. It's going to be 4/3. We repeat the same thing for the second segment. So the area of this second segment, this one here, is going to be 1 by 1. So it's going to 1 meter square meter, and then the centroid is as half and half, and then the area times its centroid would be half times 1. So it's going to be half in the x, and then half times 1. It's going to be half in the y direction as well. And then we have the third segment here. So we have the third segment. So the area of the third segment is going to be 2 by 1. So it's going to be 2 by 1. So it's going to be 2 square meter. And the location of its centroid is going to be in the x direction. It's going to be 1. And then in the y direction is going to be 1.5, or 3/2. So it's a 1.5. And then if we times it together, so in the x direction, what we have in the x direction is going to be 1 times 2, so it's going to be 2. And then in the y direction is going to be 3 divided by 2 times 2, so it's going to comes out at 3. So just know that this 3.3 divided by 2 is just this value here. So it's so that's the same thing here. After we have them, we will add them all together, the value we need. So we need this to do the calculation. We need the sum of the area. So to add all the areas together, so it's going to give us sigma A. So add all these together is going to give us 5. And also we need the sum of these two columns as well. So the sigma. So this is 1/16, and then sigma for this column is going to be 4.83. And then I will write the rest here. Then just to calculate the centroid for the x is sigma over sigma area, and we have these values already here, so it's going to be 1.16 over 5, and it gives us 0.23 meter. And the same for the y direction, it's going to be sigma over again sigma area. It's going to be we have the value here, it's going to be 4.83, and then the area is the same as 5, so it's going to be 0.96 meter. So this is how we do the calculation if we have the composite body. Now let's look at a previous example again. We will want to calculate the centroid of this object, but this time instead of split it into the 3 segments, we will consider this part as a whole and see if we consider that part as a whole, how we can do the calculation. So the first thing is that if I want to consider that part as a whole, I have to draw this whole thing first, and then draw the whole as a separate part. Go ahead and draw this shape and assume this part is not here, so that whole part is not here, that the part is representing the whole is not there. So that's what we have, something like that, and then the whole is not there, so we will get something like this, and this is gonna be the x-axis, and it's going to be the y-axis, like that. And then we will says that this one is equal to this plus that whole there. So I will go ahead and again first I will draw the x and y axis. That's the x and y, and then I will draw that hole there here. So it's going to be the whole section we have there. So it's going to be these two together. Then I will go ahead and split them. So the first part is going to be, I split this into two sections. So it's going to be section 1 and section 2. So for that particular case, I would consider this as section 1, this one section 2, and this little one here as section 3. And then I will find the centroid for each of these sections, for example. So for this triangle, we know it's there, so it's going to be again 1/3 from the base, and then this distance the same here is going to be 1/3 from the base, times 2, and for this one it's going to be half of the length, so it's going to be 1, and it's going to be 1 here. For this one, so it's going to be 1 plus half of that, so it's going to be 1 plus half, so it's going to be, and then in the y direction it's just going to be the half. Now that we have them, so we can go ahead and write the calculate what we need for each segment. So let's start with the segment 1. So the segment 1 is that triangle here. So the area for that triangle is going to be half of base times height, so it's half of 2 times 2, so it's going to be 2. And then we'll calculate or we write down the centroid location, so it's meter, so it's going to be in the x direction is negative because it's on the negative side of the x, so it's going to be negative 2/3, and for the y part is going to be 2/3, and then we have this value which is going to be 2 times that, so it's going to be negative 2/3 times 2, negative 4/3, and then we have the same in the y direction, so it's going to be 2/3 times 2 is 4/3. And then we do the same thing for the second segment, so it's going to be again 2 by 2, and then the centroid is 1 and 1, and then the centroid times the area is going to be 1 by 4, so it's going to be 4, and 1 by 4 the same, 1 by 4, so it's going to be 4. And then for the segment 3, for that segment, the area of that segment is 1 by 1, but we'll go put the head is going to be negative, and that negative is because of that's the hole, so it's the area of hole is negative, so we put the negative sign there, so it's going to be equal to -1. And then we have the location of this. This is centroid is 1.5 and half, and then when we times it, it's going to be times -1, so then negative, and then we have the half times uh, -1. Now we will add the values, all the values together. So the very last one we have is going to be the sigma of this column. So for the sigma of that column, it's going to be here. The sigma A would be, if we add all this together, it's going to be 5 again. And then here we have sigma. So we add this column together. So it's going to become 1. And the same as here, sigma would be 4.83. So the same as before. So again, it's going to divided by sigma A. So that would be 1.16 divided by 5. And so it's going to be 0.23. And the same in the y direction. It's 4.83 divided by 5, and it's going to cause it 0.96 meter. So you'll see that if we consider it as a whole, the same thing again, the whole process is the same. The only difference is that the area of that hole should be considered as a negative, and then we can do the calculation for that. We can do the calculation from the centroid.